Good. Is it possible, could we leave the lights on a little bit? If you could put the lights on a little bit, thank you. Because in this case, I want almost every slide is a separate topic, and any comments on it are basically can be done right away. And there's no pictures of any importance. Okay, we're going to, you actually have heard some of this if those of you who have been here for 5 hours, you've actually heard some of these things, and so I won't go into necessarily in great detail some of these complaints. A lot of them are accumulated from being this one of the 20 editors of the Astrophysical Journal, where I don't see necessarily the leaders of statistical methodology, but the sort of the average or the median paper. And not the ones below the median are not so good in terms of methodology. And that's really where this comes from. And Jogesh Babu, my colleague, has sort of vetted these comments to make sure that they do represent what might be called mainstream statistical views. So, of course, this is the basis of this whole discussion, that we're very well trained in let's say, differential equations for physics, but we're not well trained in the mathematics of probabilities and just the practical techniques of statistics. And as a result, we tend to use a relatively narrow suite of commonly used methods, of traditional methods. Not all of us, you understand. Just sort of a lot of studies are like this. And these older techniques are not necessarily the best or the most effective or the most powerful or the most appropriate for any given problem. We tend to sort of over-apply a few methods. Like, that's the way I fix my house. I've got 2 screwdrivers and 1 wrench, and I just use the same tool over and over again. I'm not a very skilled house repair person. And we're sort of like that. Sometimes it's actually wrong to do some things in the sense that there's a theorem that says it's wrong. So this talk is to highlight some of the common problems that one sees in the common astronomical literature and maybe suggest some improvements. So every 2 slides is a different topic. So I'm going to stop and say any comments, any questions, thoughts, and we'll see what happens. And also, these are relatively easy. This does not support vector machines advanced techniques. Okay, these are very elementary issues. So the Kolmogorov-Smirnov test is used for goodness of fit, a comparison between a univariate data set that's cumulative distribution function and a model, or maybe 2 data sets. It's called the 2-sample test, and it's used in roughly 500 papers a year. And when I went to a meeting called the Feistat 2005 meeting, and physicists and astronomers were meeting statisticians, and a distinguished professor of statistics from Harvard was speaking, and he heard that the astronomers and physicists were using this enormously commonly. He was pretty appalled. Okay. Basically, the Kolmogorov-Smirnov test is just obsolete. Okay, it is just not efficient. It's not effective. In 3 separate ways. There are 3 separate problems. The first problem is that it's very efficient in finding sort of global differences between the 2 distributions that you're studying, so that the maximum really represents like the major effect. But what if there's a difference not in the median, but rather in the spread? Then you would get 2 smaller differences, but the maximum is not really the important thing as much as, wow, there's a lot of area in here. So you want a statistic that measures the area of the differences more than the maximum. And so one of them was the Kramer-von Mises test, also from the 1930s. But even the Kramer-von Mises test has this characteristic that almost by definition, they start at 0, 0, and they end at 1, 1, both of the distributions, if they're normalized, and therefore differences at the edge and what's called the tails of the distributions are less effectively measured. So Anderson and Darling, 2 economists of the 1950s, developed the Anderson-Darling test, and here it is. It's an edge-weighted Kramer-von Mises test is really what it is. And so they wrote this down in the economics literature, and it's completely what's called distribution free. It's non-parametric. It has a global distribution. And then it was, since the 1950s, not used. And the reason it wasn't used in the 1950s is that the distribution is very hard to compute. And so they didn't have computers. So no one used it. And then when computers came along in this, let's say the 70s, people had forgotten it. And it has still not heavily, it's not widely used even in the social sciences. But in fact, it is demonstrably more, it's very similar to the Kolmogorov-Smirnov test, and it's very, very easy to run and very easy today, of course. You go to a CRAN package called, there's two CRAN packages that compute the probabilities of the Anderson-Darling test and is just more sensitive to a wider variety of differences between the distributions. And it's just as sensitive for this one as the Kolmogorov-Smirnov test. So basically, use the Anderson-Darling test and use R and CRAN to find the probabilities and don't use the KS test. That's the essence of that. Now, there's two other problems that go back to theorems which are not that obvious. The one sample Kolmogorov-Smirnov test where you compare a data with a model, it is distribution free. That means it always works no matter what is going on, only when the model is not derived from the data set. And you say, well, what? What are you talking about? I have a data set, I study it and do best fit regressions or something. I get a model, and then I want to do goodness of fit of the data set and the model, and I use the KS test. There's a theorem. It's not that it isn't a measure. It's that the probabilities that are tabulated don't apply. They're not distribution free. You can only do it if the model is derived from another data set or from some theory or something else. And I just find that to be really bizarre, okay? But what can I say, bizarre or not? My instinct that this can be done is wrong. It can't be done, or rather the probabilities don't apply. And so the answer is, well, it's not so what? What do I do? Is all of the Astrophysical Journal, is it hopeless? The answer is no, just bootstrap the original data and do bootstrap resamples and find the distribution of the Kolmogorov-Smirnov test for your particular problem. It's not distribution free, it's not a general solution, but it works for you perfectly well that day for that problem. And then you find the probability of the KS test, the KS statistic for your problem right away using the bootstrap. So it has a very easy solution, but it's not commonly known that this is a common procedure is wrong in a mathematical sense. I think that theorem is Lillefort's 1969. And this theorem, I think, was Simpson 1958 or something. I don't remember. I have it written down somewhere in the book. So these are old results from decades ago. So once again, the KS test is distribution free only in one dimension. There is no KS test for two dimensions. Now, it's in numerical recipes, and it's in the monthly notices, but it's wrong. Numerical recipes actually is rather clever. They say, it's wrong, but what the hell, let's use it. Okay, and so they have a different attitude towards what's mathematically wrong, whereas Jogesh Babu says, if it's wrong, it's wrong. That's because he's a mathematician and Bill Press is not. Okay, so it's wrong in the sense that the probabilities that you get from a multidimensional KS test are not distribution free. In fact, you can't even order things in a unique fashion in two dimensions or in more dimensions. So you can't even set the order to make the cumulative distribution function uniquely. Now, you're allowed to do something. You may go ahead and do it. Go ahead and find some statistic of interest that looks sort of like a KS or an Anderson-Darling test in two dimensions, but then do your probabilities from bootstrap resampling. And then it will work for you. For that particular figure of that particular data set and that particular thing, then you can do it. But you can't generalize it into a tabulated table. So these are three problems with common usage of the KS test. We wrote this up in a page for the Astrostatistics and Astroinformatics portal that was mentioned in my first lecture, which is now fairly large. And insofar as anything in astrostatistics has ever gone viral, this particular page gets 10 times as many hits as any other page in the portal, which makes me think that it's not being read just by astronomers, but it's being read by, I don't know, biologists and oceanographers and engineers. I don't know who's reading it. That's because we gave the page a clever name. Beware the Kolmogorov-Smirnov test. Okay? So the answer is, if you want something to go viral in this rather technical field, give it a clever name and maybe people will read it. Okay? This is examples of things that are known by statisticians that are not widely known by practitioners. The Anderson-Darling test and two cases where the probabilities that are tabulated cannot be applied in general. Okay, mini lecture's over. Any comments? The next page is a totally different topic. Yes, sir.
Is it the same case for the other test that you were saying before? It's the same.
Yes,
So
the same problems. Kramer von Mises, Anderson-Darling, same problems. Yes. Yes, sir.
Okay, but in the typical case that I have used, what I am doing is it's a one-sided test where I'm testing a model. A model is this thing a straight line or consistent with a straight line distribution is the way I always phrase it. And it gives the test always returns a probability. And if it's a 1%,
If you,
I say it's not.
if you dreamed a straight line before you looked at your data, you went to sleep and dreamed, I'm going to test a straight line, then you're allowed to do it. But if you derive the straight line from the data, then you're not, which I think is odd, but that's the way it
the
is.
supposition of constancy of the source luminosity is the straight line
That's right.
distribution.
In that case,
Therefore, yes, I dreamed.
in that case, you're doing it right.
Sorry, Eric, I'm going to
Sir.
make a comment here, and that is that the sense in which the mathematicians say this is wrong is the same sense in which everything theoretical physicists do is wrong, okay, because we approximate everything. Right?
Fine. I have no comment. I'm only telling you from the perspective of mathematical statisticians. Okay? You may do as you wish. Okay? Sir.
There is another widely used way of the KS test in which we take two populations
Yes.
and try to compare.
Same issues.
Is it-
Two
okay.
sample tests, yes.
I know that also that is not valid if the distribution is not continuous. Is that the
Yes,
case?
there may be an issue of continuity. If you've got tremendous breaks, that may be another problem, thank you, of discontinuity, of non-continuous distributions, where the underlying distribution is not doesn't have a first derivative. See, there are theorems that have assumptions behind the theorems that underlie these methods from the 1930s.
And there are versions for two populations for the other test that you mentioned, for comparing two populations, for example.
Well, the first item on this page doesn't apply for two populations. This one does apply if you want to do two dimensions. And this one, I would simply say the Anderson-Darling test is always more sensitive. It's not a question of right or wrong. It's just a question of sensitivity. Okay, thank you very much. Now, let's go to another topic. Oh, you already heard me on this, many of you, I mean, not all the same people, so let me go fairly quickly. But histograms are very good for visualization of particularly univariate distributions, but they're poor for inference. You have to choose arbitrarily the bin width. You choose arbitrarily the binning algorithm, for instance, constant width bins or constant numbers per bin or some other algorithm, and your 0 point is arbitrary. The word arbitrary means there's no mathematical guidance. You're just doing something that pleases you. Okay? There's also loss of information within the bin. You don't know if all the points are on the left side or the right side or in the middle. And you don't know if you're doing regression or something like regression. You don't know whether to use the midpoint or the centroid or something else. The square root of n, which is often why we do it, is to put these error bars on it, are not accurate when you have sparse counts. This is a case of sparse counts. Instead, people recommend, you heard me give a whole hour on density estimation. A kernel density estimation is recommended for non-parametric smoothing. And for instance, for goodness of fit, for instance, constancy or some other model, the Anderson-Darling test is recommended by my previous slide. Okay, so histograms are good for visualization, but don't use them. This is a case that dates back many years ago when it was reported by the scientists that we have a significant change from here to here. But if you simply slide the bins by half a bin, it disappears. Okay, and this is a case where this was just a binning artifact, I think is fair enough to say. So you occasionally make mistakes. The issue is usually that it's just not advised. It's not as effective. Also, for certain things like power law estimations, it's very inaccurate. It leads to low accuracy and some bias. So Here we go. Binned chi-square type regression estimates can be replaced by unbiased, unbinned maximum likelihood estimators. The answer is do your inference on the original data points. Create cumulative distribution functions and use MLEs that do point by point. And once you have a likelihood, you can do Bayesian estimation with Bayes' theorem involving priors, if you wish to. That's another slide coming up. So what I really mean is likelihood-based estimation rather than binned estimation. Don't bin unless you need to, unless there's some reason, basically, except maybe to just look at your data. It's particularly inaccurate when you have asymmetrical distributions like power laws and misuse of two-sample comparisons when you arbitrarily split the subsamples. It's just an example of a binning issue about creating two subsamples out of a single sample. The only thing that's unbiased, in my opinion, is just go to the median and split it at the median, the low and the high. But if you sort of cherry pick where to create subsamples, which is essentially saying cherry picking binnings, you can get biased results. And to continue this issue and to give more advice, I think most astronomers and physicists like histograms because of the square root of n. They know how many objects are in the bin and they know how to take the square root, and that gives confidence intervals. And they really want those confidence intervals. But as I gave an entire lecture on Wednesday, the new local regression methods, relatively new, most of them developed since the 2000s, give heteroscedastic confidence intervals from spline type regressions, from local polynomial regressions that often involve bootstrap resampling in Windows, fairly sophisticated methods. I showed you earlier today Kriging methods, which is based on Gaussian processes. Again, another method that gives not only maps of the estimations of the surfaces, but variograms. In other words, the variance of the maps that for unevenly sampled data points. And this is an example. Here's a regression estimate, sort of an old-fashioned one that just gave a line. You don't quite know how good the line is. And here's a new one that gives the line with the confidence intervals. You can see right there, it blew up in terms of your uncertainty, whereas down here, your certainty was pretty good. So this is a much better, newer approach. Here's an example of there are 5 books written in the last few years on non-parametric regression that I know of, and this is one of them. That, by the way, chapter 1 is histograms, and chapter 2, 3, 4, 5, 6, 7, 8, 9 are the newer methods. Okay. Any comments then about overuse of binning, histograms, or other forms of binning? Sir.
I have a data set with like a few hundred data points that are all confined physically between 0 and 1.
Mm-hmm.
And I would like to present it in a paper.
Mm-hmm.
So a histogram would be a very obvious method. The problem is I tried using kernel density estimation, and what happened is that the estimated density function, it was non-zero outside the zero interval.
Yes. The KDEs do have to treat edges correctly, and some do and some don't. Kernel density estimators. Okay, I don't think the statistician would object to using histograms. They use them themselves for visualization, for looking at your data. It doesn't work very well in high dimensions, but univariate, it works very nice. But just not for inference. Okay? So I don't think anyone would object for visualization. Okay, I have several slides on regression, so maybe we'll go slide by slide. I'm not sure exactly how to do it. And you've actually heard, some of you have heard who were with me on Wednesday afternoon, we did regression, and you heard me say some of these things, but I'm going to package it all together here for this audience. So we often devise a chi-squared like statistic, which is really it's the sum of the squared residuals between the data and the model divided at each point by the square of the measurement error of each and every point. And then we minimize that in what is might be called a weighted least squares, weighted by the heteroscedastic measurement errors. That would be the way they would phrase it. We call it chi-square minimization. They would call it weighted least squares, and in order to find the best fit model. It ends up this is fine under certain restrictive conditions. Okay, the models have to be Gaussian. The models have to account for all of the scatter of the data about the model, and the model has to be right. Well, it's this model specification. Okay. So it ends up that there's nothing wrong, except we often violate these conditions. Now here's just an example. Here's a model that's done by weighted least squares, as in the usual fashion. But you can see that the scatter is not fully accounted for by the measurement errors. So they weighted by these little error bars. Basically, I mean, that point pulled the regression up for, let's just say, no good reason. Or at least it wasn't attributable to the measurement error. And so that really was not a good procedure for this particular case. In addition, if you actually look at the measurement errors, they're almost all the same, which means it's homoscedastic, in which case you just divided by constants, essentially, something you can bring out of the sum, and it didn't even matter anyway, so you might as well have just done least squares without any weighting at all. This was just an example of basically an ill-conceived way of doing the regression. Okay? So if you okay, thank you. That's one issue there. And here's another issue. Parameter estimation, and particularly parameter confidence intervals, may be biased and even possibly completely wrong if the model is misspecified. Misspecification is a technical word. Okay. Within the context of this minimum chi-squared, it means the reduced chi-squared is greater than 1 or even less than 1. Okay, so when the measurement errors are incorrectly specified or are not fully responsible for the variance of the response variable. And so only when chi-squared does approach 1 can you get the right parameters and get the right confidence intervals of them. And you don't even know exactly how close to 1 you have to be for this to be true. So this is a big problem for using what's called minimum chi-square regression. And people submit to the AppJ articles where the minimum chi-squared is like 3 or 0.3, and then they tell you the parameters, and I, as the editor, have to say, I mean, you can't tell me the parameters for that. That's not science. It's an arithmetic result, but it's not a scientifically valid result because the model's misspecified. And the authors don't like that because they think minimum chi-square is the only technique they know, and it's in Bevington and numerical recipes, and they know it, and they don't realize that model misspecification is a critical issue. By the way, it's not that easy to do with maximum likelihood either. Model misspecification is a broad problem. If you misspecify the model, the parameter estimates are not necessarily scientifically meaningful. Even if you want them, then you may not be able to get them. Okay. Another thing is that it may look like chi-squared. You may think it is chi-squared, but it's not chi-squared distributed. In fact, we should never have ever said that summation of x sub I minus x model, the quantity squared over sigma sub I squared. We should never have called that chi-squared. What is the statistician has called it x squared, where x squared is chi-squared distributed under certain conditions. Under other conditions, it's not chi-squared distributed. So we sort of fooled ourselves because we happen to call it chi-squared. That is chi-squared distributed. Most important is a theorem of 1955 by Sherman and Lehman, two of the greatest statisticians of the 20th century. Lehman recently passed away. Chernoff, again, 90 years old, from MIT. That the probabilities, particularly the degrees of freedom, are well established only in restricted situations, and in particular, it requires that the bins within which you calculate these sort of error bars and calculate the values have been determined before you did the experiment. That you put bins on the floor, and then you put data in the bins, and then you wanted to do it. It's called the multinomial experiment, Pearson 1900. And not chosen later, not divided later. Now, in this particular case, it happened to be a time series, and that is chosen by the experiment. But other cases, people divide them up later, and then the degrees of freedom are uncertain. It may be chi-square distributed, but with uncertain degrees of freedom. In other words, the probabilities are unknown. You can't do confidence intervals correctly, reliably. This theorem is not well known. Okay? It's in chapter 1 of the book on chi-squared estimation, but we haven't read the book, so we didn't know that. So what do you do now that I've said there's all these problems? Well, the answer is you just don't bother waiting by them. And you might say, well, that's one possibility. I mean, it's not the only way. I say, but my measurement errors, I love them. But you have scatter that's due to the objects. You have scatter that some of that scatter is due to the measurement error. So what? Just take the scatter. That's what most statistics is. They do unweighted least squares, and they just take the scatter. The scatter is part of the model. It's those epsilons in a regression formula I showed earlier on Wednesday. And they don't specify what portion of it is measurement error or what's not. If you want to specify, then there's certain hierarchical models that can be written down, either frequentist or Bayesian solution, doesn't really matter, that are called measurement error models or errors of variable models that are a little more complicated than this. The best one that we know of is Brandon Kelly's 2007 FJ paper, who writes down a complicated likelihood that includes the heteroscedastic measurements and other sources of variance with, in his case, it was a linear model, but it could be a nonlinear model. And his approach to the problem is, in my opinion, a mature approach, and really sort of subverts all of these hassles that we have with the, I guess, immature approach of trying to adapt Pearson's chi-squared test to a wider range of problems that doesn't really apply. Okay, so that's a general criticism of chi-squared regression. Again, when statisticians hear that a whole community is using this strange method that basically dropped out of favor around 1940 everywhere else, they're pretty upset. They don't think we should be doing it. It's not always wrong, but it has pitfalls and problems, and that's not people using likelihoods. Okay?
Up here?
Yes, sir.
Is there something that we love to do when we study young-stellar objects, is to take the data and fit over models of stars with disk accretion and so on. And usually you verify the fit using the chi-square. I mean, everybody does it. I did it a lot of times. So what you...
I would say it is doing something you want to do. You're minimizing some differences, some variances. You're weighting it in ways you want to weight it. Go ahead. I just wouldn't believe the probabilities. That's my opinion. In other words, you don't know how to draw the confidence intervals very reliably. Sometimes the tabulated probabilities are appropriate, but often they are not. But is it doing what you want to do? Often it is. That's my personal advice. It's not always wrong. It's just not the way it's recommended.
Okay,
Sir.
so now I'm asking the editor of the AppJ, what is the appropriate way that he would prefer? I mean, the thing that I measure directly is the chi-square residual. Then sometimes I'll throw that into some sort of cast that as a probability. But as I do that, I am moving further away from what I've measured to something that is presumed. And as Mario said, you fit the thing. You have a chi-square measurement. That much is known with certain assumptions. Should we just stop there, or can we?
Well, it's certainly better to be explicit about your assumptions and to be aware of the possible pitfalls. I would say if you can argue that the errors are Gaussian, that the model is correctly specified, and that all the scatter is due to the measurement errors, then you can argue that I satisfied the conditions and everything's okay. Sir.
That's kind of circular because you're testing whether the model is correct.
It's a question of, is this procedure valid for your problem at hand? We just assume that it's always valid because someone named Philip Bevington told us it put it in a book. 40 years ago. And what I'm saying is that it's in a book, and it's sometimes valid, but don't take it for granted. Sir?
Yes, so if you go back to the RVA data, it is obvious if you look at it and you look at the error bars that your model and your estimated errors do not account for scattering the measurements. So what if I just say there's some astrophysical jitter? I assume that it's independent.
Sure.
Of data point data.
That's a hierarchical model. Kelly has that. Errors and variable models have that. Then you make a hierarchical model.
So is it valid to just estimate the amount
Sure.
of astrophysical jitter?
Sure. It's part of the model. Exactly right.
Has to be one.
Right. And I don't have time to go through it. You should read Kelly. There were earlier least squares attempts to put it in. Fit XY is one of them, and Tremaine has one. There's a few. And all of those are not as good as Kelly's. Kelly shows that his method's better, more accurate. Okay, here's just general advice. Again, I gave it earlier on Wednesday, I believe. That when you do a regression, chi-squared or otherwise, and you have a best fit and you want to look at it, look at your residuals. Study your residuals. You can only learn things about looking at your residuals. How much of the original variance is reduced by the model? If the model reduces the residuals by only 30%, well, it's not a very effective model in understanding the scatter in the data. If it does 90%, it's very effective. In multivariate terms, looked at the adjusted R squared and Mallow CP. These are very well known in multivariate analysis, in the social sciences, and surprisingly not well known to astronomers. Okay. Are the residuals autocorrelated, or do they have a whoa? And I showed one example of that in Corman's The Elliptical Galaxy on Wednesday. And where autocorrelated residuals, he noticed it. It's not that he didn't notice it. He did residual analysis, actually, which was to his credit. In that case, there's a lot of science, perhaps, in that residual analysis. What isn't accounted for by a searchic model might be interesting astrophysics. Are the residuals normally distributed? If not, take a look at quantile regression. And I gave 2 or 3 examples of quantile regression on Wednesday to show not just how the median goes, but also how the 25% and the 70% go, or even if you have a lot of data, the 10% and the 90% quartiles. So you can regress different parts of your data if you have a rich enough data set and if it's non-Gaussian in behavior. And then you always should check for outliers, for individual points that sort of are pulling it away. And I don't claim that you have to throw them away. Maybe they're scientifically important. Maybe they'll tell you something. Maybe they don't belong in the sample. Maybe they do. You think like a scientist, but at least find them. See whether individual points are having a larger influence on the regression fit than others. And in multivariate statistics, it's known as Cook's distance. We never use Cook's distance. It's all built into R, and it's built into SAS and other programs. It's well used in other fields. We should be aware of these standardized residuals and leverages and Cook's distances. And then we should use robust techniques. Robust regression is an enormous field initiated by professor at Harvard, Peter Huber, 1960s, in statistics. The modern treatment, mathematical treatment of how to reduce effects of outliers in various ways. And if you don't like Huber's approach, use Roussillon's approach. There are other ways of doing it as well. R has an entire page of, 70 packages that do nothing but robust regression for ways of treating outliers. The main problem is, which one do I do? And try a couple and see if they come up with good results. Results you like. There's not much mathematics to guide you on which procedure to use. There's some mathematics, but it's not perfect. Okay, any questions about residual analysis? I think it's just good advice for everybody. No matter how you do your analysis, your regressions, study your residuals and make sure you're satisfied. Ideally, your residuals are small. Maybe if you have no measurement errors, consistent with your measurement errors, and that they're not autocorrelated. They don't have waves and ripples and structure, and they're Gaussian. That's ideal. That's not always ideal. Your data set may not be ideal. Okay, now we mentioned misspecified models, model misspecification. It's a huge problem. It's a big issue talked about in econometrics. It's a big problem talked about in other fields, and it's a big problem for us. Okay, and there's just a couple comments I can make. I think I mentioned it briefly. If you don't even do regression if you don't have a response variable. If you have 10 variables and you know you want to say that the sixth one is the one that you want, that you're interested in, how does redshift depend on photometric colors, then you do photometric redshifts and you're predicting redshift. It's a regression. If you have 10 variables and you say, all these different properties of spiral galaxies, they're infrared, they're X-rays, they're radio, they're morphology, just tell me something I want to understand spiral galaxies. Well, I don't see where the response variable is there. Then don't use regression. Principal component analysis and its nonlinear enhancements are good examples. Symmetric regressions, if you just have X and Y and you don't want to prefer, then do a method that is asymmetrical between X and Y, such as the ordinary least squares bisector. And we wrote some papers 20 years ago on this, and they're not bad papers, they're not very sophisticated today, saying that the bisector regression is actually pretty good if you use the right error analysis, which we give. One way of finding model selection is to use the Anderson-Darling test from a few slides ago to evaluate goodness of fit. If there's a problem in the field, is that the Anderson-Darling test cannot be done in high dimensions. We can't even do it in 2 dimensions uniquely. And so we have troubles with model goodness of fit in higher dimensions. And to my knowledge, that problem has not been solved by statisticians. And they don't talk much about goodness of fit, to my irritation. And I've read only 2 books on typically the fields. There's maybe 10 books for every page. I've only seen 2 books at all, ever, on goodness of fit. And they don't seem to come to agreement. Instead of being textbooks with consensus results, it's more debates between experts. And that sort of irritates me. But one thing to do is to use cross-validation, a bootstrap technique. Cross-validation, you take some of your data and put it in your pocket, don't use it for your regression, and afterwards just take it out of your pocket and see how it does. A bootstrap is to resample with replacement your original data over and over again, and use these approaches for validation. So I think that maybe a more general approach, the Anderson-Darling only works in 1 dimension. These are more general approaches to validation, to goodness of fit. So study your residuals and try to do validation. And then discuss whether Occam's razor has been appropriately addressed. Is your model elaborate enough that you captured the features, the residuals look clean, or am I too elaborate? I fitted all the little details and I really should simplify. And this is where there's still a debate. Should I use the Bayesian information criterion or the Akiyiki information criterion? What's the penalty to the likelihood in MLE theory? But this one is also from Bayesian theory. Should I use the adjusted R squared, which is a least squares version of these, an earlier version of these things? The details are still debated by statisticians, but we should at least be using something equivalent to a penalized likelihood information criterion for model selection, at least trying it out. And that helps you decide. The simplest one is, of course, the likelihood ratio test, which is, I think, my 2 slides from now. And there's a warning against that one. So I did not mention the likelihood ratio test here to evaluate different models. Okay, model selection and goodness of fit. Okay, little more complicated than most astronomers treat. It's not that they never do any of this. In fact, they often do some of this. But it's not in our minds that every time we do a regression, we should do residual analysis and really work on validation. Comments? Okay, other issues? I mean, I couldn't figure out what to call this page. Watch out if your regression results change when you arbitrarily change your variable units from kilometers to seconds to centimeters per second, or when you take a log or you don't take a log. You don't want your science to depend on arbitrary choices you made in your methodology. If there's any theme in my whole lectures, you don't want your science to depend on arbitrary decisions as much as you can. So you should do a lot of non-parametrics before you do parametric testing, and maybe fiddle around a little bit with your variable transformation. Make sure you're not quoting a result that's completely dependent on some choice that's not a good, I mean, it's not being a bad choice, but it's arbitrary choice. Now, another one is just a habit. We like to take a 10-dimensional problem and view them as a sequence of bivariate problems. There's even a beautiful matrix of bivariate plots. Even I showed one yesterday in my lecture. They're very useful. But most of the regression methods, Bayesian, frequentist, likelihood-based, least squares-based, almost all of them are mathematically derived using linear algebra. You can have 1,000 dimensions. The same method applies. It's no restriction to 2 dimensions. It's just easy for the eye. So just be aware that if you have a multivariate problem, maybe you should do a multivariate analysis. This is basically a no-no. Okay, if you happen to do regression for variables that are almost on purpose chosen to be not independent of each other, like you have b minus v and v minus I, you can go ahead and show the plot. You can go ahead and make scientific inferences. But if you're doing a regression, the meaning of those parameter fits mathematically is, I have no idea what they mean. Okay, because the theorems underlying almost all the methods are the variables are independent of each other. Okay, great caution. And then there's just all sorts of variations of often on the category of nonlinear regression. There's a nonlinear regression method known as Poisson regression, where the y response variable is a counted variable, so a number of counts, number of events of some sort. So we're not supposed to do regular regression. We're supposed to do Poisson regression for that. There's actually a lovely example where the response variable has only 2 options, 0 or 1, or yes or no. You can imagine it's very commonly used in social sciences, where they say, excuse me, are you Republican or Democrat? Are you male or female? Okay, yes or no. And so there's a lot of regressions that have to do with that. And that's called logistic regression, the whole field. And then there's categories, okay? Democrat, Republican, independent, or green, okay? And there's regressions for that too. So be aware that you don't need real numbers to do regressions. You can have categorical variables on either side of the equation, and the methods are different. You have to read a book written for social scientists, and it will tell you how to do it. Any comments on this page? Sir?
I'm going to jump back at the b minus v, v minus I
Yeah.
thing, because we get these distributions where we look at a source, and the source varies along those 2 channels, along those 2 colors, and we want to get a measure of that of the nature, the trajectory is what I called it, of the variability. A least squares fit or a linear fit appears to be appropriate. The slope changes linearly. I can fit that to a number, a slope.
Yes.
The error bar, and that when I do it, I can evaluate.
Okay, don't even continue, Scott. I have no idea.
Okay.
No statistician ever puts that in any book whatsoever. So I have no idea what.
But the issue is that because the 2 samples are related.
The 2 variables are
related.
constructed to be dependent on each other.
Right.
Therefore, the theorems underlying all regression techniques that I've ever heard of don't apply. Try Thiel-Sen regression. Okay, I can't go on. Okay, there's some non-parametric regressions that maybe don't have theorems that rely on this. I'm not sure about that. Don't rely on that. Okay, sir.
So this is you're only talking about response variables correlations with the independent variables.
That's right. That's what the word regression means.
Right. You can always do x and x squared as 2 variables and regress against those 2 for a y, but y should be independent of
That's exactly right.
Okay.
Precisely right.
Okay.
Right. Absolutely. Sir.
One thing related to the same point is that often we're regressing y that has a measurement error and x that also has a measurement error. So
Yes.
one of the things I like
Almost
about,
no methods available for that.
One thing I like about Brandon Mattelli's paper is he actually shows if you ignore the error in the x-axis,
You can make.
get a biased result.
Oh, he wrote this gorgeous paper more recently on the Herschel dust beta, where not only was it biased, but the standard result was actually in the wrong direction. They actually got the slope in the minus slope instead of a plus slope. And he solved a whole little field, something called spectral energy distributions. Please be aware if you're doing SED analysis. Look, not Kelly 2007, it's Kelly 2010 about. And it's a brilliant paper. It's really cool. Okay. And of course, it's very Bayesian, if you like that. Okay, now here's a warning. It's very closely related to the point about model comparison, elaboration of models. When do I model validation and model comparison, right? And there's a famous test from the 1940s called the likelihood ratio test. It's a classical likelihood-based test to compare the relative validities of two models for a single data set. It goes back to people like Fisher and Abraham Wald and other classical work. There we go, 1930s. Okay, it's particularly used for nested models when you have a simpler model and then a more complicated version of the model, and you want to compare whether you need this. First of all, it does assume the null model is true. That's the model specification problem. But if it is, then this statistic is chi-square distributed, at least asymptotically, which means for large n, for large number of points. However, a certain group known as CHASC, in other words, Vinay Kashyap, Aneta Smiergowska, and their colleagues, David Van Dyke being the professor leading them, they wrote a paper some years ago, a dozen years ago now, that very much cautioned astronomers, very much like my lecture here, that we tend to make a mistake. We tend to violate a theorem that dates back to this early work. And that is that we sometimes use it to help decide whether a parameter exists or doesn't exist. In other words, some parameter of the model is or is not zero. Well, it ends up that this basically violates the theorems of the 1930s, and it's not even asymptotically chi-square distributed, even with infinite data, near the boundary, any boundary of the parameter space. And you should use alternative procedures, such as the Bayesian information criterion, or its more elaborate version, the Bayes factors, or the Akiyiki information criterion, but not the likelihood ratio test. So this applies to some dozens and dozens of studies they showed are basically violating a theorem, and they're very wise in doing it. I want to praise not only this astrostatistics group here at Harvard for writing the paper, but in this particular case, you just deserve a lot of credit. This paper's been cited a couple hundred times. In other words, a lot of people of our community have read this paper and say, oh, Protasov and company say I shouldn't do this, I'll do something else that's better. And it's really nice to see. This is an example of a problem that has been, I won't say solved, but where there's been highly skilled people, cross-disciplinary people, telling the community of the problem, and the community has listened quite a bit. Any questions about the likelihood ratio test? Any comments from Aneta or Vinay? Okay. Thank you. Okay, that's my comment. Okay, here's a little comment by me. It's not very profound. Many astronomers have a nearly religious belief that 3 sigma criterion decides whether something's scientifically valid or scientifically not valid. But be aware that it's equivalent if it is a Gaussian distribution, your probability that at 99.7%, it's just arbitrary. Okay, I found an astronomy paper that talks about it. There it is, Jasper Wall, author of one of the astrostatistics books, but absolutely no one has cited that paper, so it clearly was not influential. It more like talks about what's in the air. This is probably more influential. This is the founder of quality control statistics, but surely no astronomer has ever read Stewart or ever took a class in quality control, so I don't know how his ideas, which affect manufacturing quality control, came into astronomy. I have no idea how this happened. Okay. Curiously, the social sciences, the biomedical sciences, and other societies use a completely different criterion. They use 95%. That is attributed to a famous book by R.A. Fisher on research methods for researchers. Particle physicists are very nasty on themselves. They require 5 sigma before they'll declare a new particle. Okay, maybe it's what Vinay mentioned, Carl Sagan's quote or something. They need extraordinary evidence to make an announcement they have a particle because a Nobel Prize depends on it, right? So it was really interesting last year in 2012, I guess a little more than last year, when the Higgs boson was coming. They knew when they were going to reach 5 sigma, so they would say, well, in 6 weeks we're going to have a press conference. In 2 weeks, then they had a press conference, and then they announced it. It was really funny. I thought, okay, that they sort of knew it. And then I don't know if you know anything about how modern manufacturing business goes, but they're all wedded to Six Sigma these days. And Jack Welch of General Electric. Do you know any of these people? Okay, they made their billions on Six Sigma. It's not silly. Think of a piston in an automobile that has to go up and down trillions of times without braking. Maybe you do need Six Sigma reliability. Okay, so they do it. So the point is that there's no consensus at all. 3 sigma is just a choice. And also the difference between sigma and the probability assumes that the Gaussian distribution applies to your particular problem out to the distant tail, and you have no idea whether your data set is Gaussian out to that tail. You have no idea that's true. So you're just, I don't know, it's just a habit. Okay, and someone complained that the Bayesian hypothesis tests don't even give you probabilities. They say, well, if the Bayes factor or the BIC or one of these things is, between 3 and 5, it's a moderately good result, and between 6 and 8, it's a strong result, and greater than 8, it's a very strong result. And you complain about that, but frankly, it's an illusion that you actually know this probability precisely, and so really there's no magical difference between 2.9 and 3.1. I don't have any advice. I'm not telling you what to do. I just want to say that you live in a murky world. It's not clean. And you're scientists. You're not statisticians. So, I actually don't think 3 sigma is crazy. I think if we did all of our science with 95%, we'd be making a lot of mistakes. And if we did all of our science with 6 sigma, we wouldn't publish anything. So I actually think we're probably more or less where we want to be. So I don't want to complain about what we're doing. Just be aware that there's no foundation to it. It's a choice by us. We're allowed to choose. We choose. Sir?
The bigger point here, though, isn't that there's a general cost function associated with converting these kind of distributions into
Yes.
inferences?
But the question is whether it applies to your data set.
Yes, and the question is, for example, if you're going to kill somebody of cancer, then it's not a very symmetric cost function, and it makes no sense. You know what I'm trying to say?
Okay. Okay.
You have to ask the question.
Okay. If you have really, really, really Gaussian data, then maybe that conversion is correct. Okay, now for my most challenging page. This is 2 pages long, then we'll discuss it. This is the one where I expect to get a little bit of feedback from you guys. When uninformative and flat priors are used, Bayes' theorem is basically giving the mean of the likelihood function, not the mode of the likelihood function. The mode is the best fit value, the best fit single value. The mean is where you're averaging over. Now, if it's just a little Gaussian, the mean and the mode are the same. But if you have funny structures around, the mean is going to be pulled off of the mode. And so it could be that those things pulling it off the mode are scientifically uninteresting. And maybe you really don't want the mean. Maybe you really want the mode. So you just, as a scientist, you have to consider what you want. Okay? Do you want to average over structure in the likelihood, or do you not want to average over the structure using a flat prior? And if you have an interesting prior, or even various choices, arbitrary choices of priors, you have to definitely discuss how your posteriors depend on your priors. So the journals are beginning to, in an editorial sense, the referees and editors are beginning to tell you, thank you for section 3.2. You've done a nice Bayesian analysis with an uninformative prior. Tell us what the result is for a few other priors. And often your result's fine. Often your result doesn't depend on this. And sometimes it does. And you don't want your science to depend on arbitrary choices. Okay? So when you have no ancillary information other than the data that you're analyzing, and the likelihood structure is simple, most statisticians recommend to choose the mode. Okay? This was recommended by Fisher in 1922, and most scientists in most fields choose the mode, the best fit model. Okay? Is it the only thing to do? No. You can choose the mean. But be aware that it's not the same necessarily. Now, when you have scientifically prior information, as Vinay actually discussed, from prior observations. Maybe I think you used the word daisy chain your science forward as you get things. It's very clever, okay? Or if you have scientifically important multimodal structure, you have very bumpy, lumpy, complicated posteriors, and the mode may not really tell you what you want. Okay, then without a doubt, you need Bayesian inference with all of the apparatus of sampling high dimension or some dimensional parameter space, possibly high dimensional space. Now let me give you an example. This particular picture came to me as an editor, and it was on Bayesian model fitting with MCMC calculations, and here was some data. I don't remember what it is, and they did what's called a mixture model. They took two different things with, I don't know if it's a point spread function or some sort of a known distribution. Here's the data, here's the model, here's the residuals. Oh, look, it's a great model. So I said, thanks very much. I have no complaint about what you did, but, are you aware you could probably do it with MLE, maximum likelihood? And so they resubmitted it, and they did it with MLE, and it came out great. In fact, the MLE, because it's a linear model, is just the same as minimizing chi-squared, or really just least squares, okay, with model selection using the BIC. Whoops. Oh, I shouldn't give the authors to this. I'm sorry. Okay, because I'm complaining sometimes. I'm not complaining, actually, about this. Now, here's an example of where, look at the multimodal, weird, bizarre likelihood. That is not a simple Gaussian posterior, okay, of just these two parameters. And this particular cosmological model had, a whole bunch of different variables, each of them with really weird-looking posteriors. It was a very nonlinear problem with completely different data sets it was being applied to, and the model and the data comparisons were really very complex. It was a big, messy problem, okay, in this case of galaxy star formation over cosmic history or something, with complicated posteriors. And in this case, you have to take the full Bayesian apparatus, analyze it to you, see your posteriors, and good luck in making scientific inferences. It's not clear the peak of anything means anything. You're learning about your very complicated science in doing this. And by the way, this particular group at University of Massachusetts, under Martin Weinberg, has actually provided something called the Bayesian Inference Engine. It's a software package that is designed to help you with very complicated problems in Bayesian inference. And there's quite a number of others. There's another one from University of Cambridge called MultiNest, again, for multimodal likelihoods. So there's certain astronomical, astrophysical, and astronomical groups who are really very sophisticated in Bayesian analyses and are giving tools and strategies for very difficult, complicated problems that really cannot be addressed by maximum likelihood estimation, the old-fashioned way. So, by the way, if you want to compute an MLE, one does it through the expectation maximization algorithm, EM algorithm, and it's often done in 50 iterations. The EM algorithm has a theorem that every time it turns the crank, the likelihood has to increase. So it goes boom, 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 and it finds the peak very rapidly. There is no theorem for that in MCMC. You can run 1 million MCMCs, 1 million calculations of your likelihood, and there's no guarantee you're going to converge at all. So people, I don't know what to say. People are too in love with MCMC computations, but realize they're cumbersome, they're a little dangerous, and they are unnecessary for simple problems. Simple problems, do MLE. Okay, any comments on this view? This view is not ubiquitous. There are some statisticians who say Bayesian is the way to go for everything. They are in the minority of the statistics community. Most of them are what Vinay said at the very beginning. Most statisticians are Bayesian when it's appropriate and frequentist when it's not, they're not. And they actually don't think too much about the theory, the philosophy problems. How many physicists think about the philosophical problems of collapsing the wave function? Einstein-Rosen-Podolsky paradoxes. They don't think about it, they go ahead and they compute. Physics works. So statisticians are sort of the same. Most of them are not thinking about philosophy of Bayesian versus frequentist. They say, you need a Bayesian analysis, or, let's just do a simple MLE. By the way, the MLE is the least squares for linear models, which is a broad class of models. They certainly do least squares. It's easy. Life is not always hard. Sometimes it's easy. Okay, thank you very much. Oh, no. Thank you very much. That was thank you very much for not throwing tomatoes at me. That was what that was. Okay, that was great. Okay, here's another comment I made earlier. I am coming close to the end. There's 2 pages to this one. The Friends of Friends algorithm that was developed here at Harvard in CFA in 1976 is basically not recommended by any statistician for finding a hierarchical non-parametric clustering because it gives spurious chaining of clusters. And every book in the field knows this, states all the tests that do this. They recommend average linkage or Ward's criterion instead. It's technical, but the point is that astronomers are using Friends of Friends over and over again because it's familiar, because it was done at Harvard astronomy, it must be right. But unfortunately, these then young Harvard astronomers didn't know any statistics. If they'd only looked in the 1950s statistics literature, they'd know that this is not the right. They'd know what it was called. It's called single linkage agglomerative clustering, and they would know that it's not appropriate for many problems. Here's a simple book. That's a very useful book. It's an undergraduate level book, 5th edition. Anyone doing any sort of hierarchical clustering or any kind of unsupervised clustering at all should be reading the book. It takes about 3 hours to read the book. It's not a very difficult book. Okay? So we would just not make mistakes if we read some of the books. Okay. Now, here's another one. This is very famous, and it happens not to be Harvard, where a curved separation was made between here and here. It actually reminds me of support vector machines doing curved surfaces to discriminate between supervised clusters. And these are essentially decision trees. And as I showed this morning, there are mathematically and procedurally organized ways of constructing decision trees and pruning decision trees developed by Leo Breiman and his colleagues at Berkeley over many decades. That there's boosting and bagging that improve the trees and give you reliability of the trees, and random forest is the implementation of that as of the early 2000s, and random forest is like a winner for many, many problems of supervised classification, and so really we should stop doing what's called sort of visual heuristic or subjective classifications as Vayeux and Harstebrock did, but do instead more organized ones. Now, I mentioned in my question to Vinay just a half hour ago, I said, Vinay, is your work related to something called false discovery rate? And this is an interesting problem. It occurs in a selection of astronomical problems.
Sorry, can I interrupt for a
Yeah.
minute? I actually asked David Van Dyke in the interim.
Oh, yes.
And he said he doesn't think there's any.
Okay, it just coincidentally has 2 parameters. I got it. Thank you. That's reasonable. Okay, well, this one does. This is when, let's just say you have a very large data image or data cube, and you want to find structures, and the point spread function is small. You're making a decision. Is there a source there? You're doing a question hypothesis test 1,000,000 times. Well, when you do 1,000,000 times, and the idea of like 3 sigma, it no longer works. We already know that. We often do 5 sigma. We don't know how to control the false negatives and the false positives in a reasonable way. And then here's radio interferometry, you get non-Gaussian wobbles and all sorts of problems, and it's not even Gaussian data noise. So it ends up, there's a traditional way, which is called family-wise, a family-wise control, they call it Bonferroni. But it's very conservative. It says, basically, it's the kind of thing, excuse me, I'm going to speak to the X-ray astronomers in the room. It's the kind of thing that Peter Freeman did when he said, I'm going to tell you the threshold of the wavelet threshold, so there's only 1 false positive per CCD, okay, which is P of 10 minus 6 or something. And it's very conservative. Okay. So the point is that it's not clear, do you want to be generous, you want to be conservative? What Benjamini and Hochberg, in a very famous statistics paper in 1995, wrote down is that let the scientists decide. Let there be 2 parameters. One of them is the significance level of the detection, and what is the desired ratio of type 1 to type 2 errors, false positives to false negatives. And you actually specify 2 probabilities, and you can say, well, I want to be absolutely complete. I don't want to miss a single one of my Seaford galaxies. So I'm going to choose a lower threshold to make sure I don't have any false negatives. If I get some mistakes, I don't care. Or I say, oh, I have to follow this up with 8-meter spectroscopy. I'm willing to give away some of my sample to be really, really clean. I don't want any false positives. So you can choose your own judgment. They would call it a risk function. You choose your own risk function based on your scientific goals or purposes, whatever you might want to call it. And FDR gives you a way of doing it. It's quite simple. Take a look at the Wikipedia page. It's really not very difficult for simple FDR. There's actually dozens and dozens of papers on this by methodologists in the last decade. And we should be thinking about it when we do things like faint source detection. So my last slide is just et ceteras. As an editor, I just don't like people telling me my hypothesis test has a probability of 81%. Well, really, I just want to know it's anything above 5%. That means that the answer is no. And don't tell me it's 10 to the minus 13 and not 10 to the minus 16. The answer is yes. These tails are not known. I mean, the calculation gave it to you, but there's no meaning to that 10 to the minus 13 because then no one knows those tails apply to your problem. Okay. And then don't tell me 4 digits of precision of your value of chi-squared or its probability. I mean, no one knows that 9-2 at all. I mean, you barely know the 1, okay? So just don't exaggerate just because your calculator tells you these numbers. They don't have much meaning. This says there's no significance to hypothesis. This says it's very significant, and this says this is the value. 1 digit's usually enough. Okay, I personally hate the fact that we refer to MCMC by the last cosmology paper that used MCMC instead of referring to a textbook on MCMC. Okay, how about the Handbook of MCMC edited by Gelman, distinguished statistician at Columbia? Okay, why not that one? Or go back to the original Metropolis Hastings paper in the 1950s. But there are many textbooks. You should be looking at a textbook and referring to the textbook to show that you've read the textbook and to encourage others, and that's the correct reference. And the previous astronomy paper is not. You can start with an elementary book like Feigelson and Babu and start with Wikipedia and start with the other elementary textbooks that should be now taught in graduate schools. But the best part of my book are the recommended readings of the textbooks, of the real textbooks. We're just an entree into the literature. And then, this is not a strong comment, but there's a debate as to whether or not we should be publishing codes, statistical methods, a little more detailed. Publish in an appendix your SQL commands for pulling out data sets. Show us your R or your MATLAB or your Python algorithms, either pseudocode or direct code if it's simple enough, to improve reproducibility. You should know that Nature Publishing has now clamped down on its biosciences literature. Every paper is now being vetted by a statistician. And that's because they found that 47% were reproducible and 53% weren't, and they got upset. Okay? I mean, lives depend on cancer treatments. So you don't want 47% reproducibility. Lives don't depend on your stars. Okay? You get a mistake, you made a mistake. Okay? But nonetheless, this is an issue being discussed in science publishing without really much resolution. So I'm a little over time. I want to finish here. There's a vanguard of astronomers, which includes here at Harvard Statisticians Group, who use and develop advanced methodologies, but most studies in most articles are using still a small suite of familiar methods, and you need to just become more informed, more involved, read elementary texts, more advanced texts for both data analysis and for science analysis, for instance, regression problems and clustering classification problems, and that's why I'm here for 3 days. And for those of you who sat in and actually listened to me for hours, young and senior, I'm really impressed that you did this. Okay, because that's my goal is to improve this education for our field. But it's not that hard to identify some common weaknesses. That's what this lecture was about, and it's not that hard to improve them. It's not rocket science, ladies and gentlemen. It's not as hard as astrophysics. Statistics, look, sociologists learn this stuff. It's not that hard, okay? You just got to get a little bit of trained, have a few statisticians like David Van Dyke, like Yogesh Babu, to sort of coach us on the side. And you need to know R so you can implement things really fast. If those of you who heard me earlier just saw how much. Bingo, bingo, bingo. You can do so much in R to try things out and to learn about how your methodology is performing on your problem with your data set. So now I will say thank you very much for being such a good audience. I don't think there are any questions at this point. So good